All right, I think we're gonna just go ahead and we'll just go ahead and get started.
Great. Well,
All right,
thank you,
welcome
everybody.
everybody um, to the North Atlantic Fire Science Exchange's student webinar series. My name is Eric Evanson. I'm the Science Communications Specialist with NAFSE. And again, I'd like to welcome you to our Spring 2024 student webinar series. The goal of this series is to connect students with the fire and forestry community to develop positive and productive working relationships, as well as sharing knowledge and information. And so today we're super excited as we wrap up our spring 2024 season to have with us Trevor Roper from Columbia University. And his talk today is going to be the impact of controlled burning and forest thinning on the recovery of tick populations over time. And so the way it's going to play out is we'll have Trevor give his presentation first, and then we'll follow up with a question and answer session at the end. And then now, if you do have questions during his presentation, feel free to pop those into the chat, and then we'll come back to those at the very end. And then we'll follow up with some final thoughts on our student webinar series. And then let's go ahead and just take a moment to introduce ourselves in the chat. Perhaps put your name, your affiliation in there. If you want to put your location in there, feel free to. All right, welcome, Amanda. Eileen is with us from Columbia University as well. Welcome.
So Eileen actually helped with this project. She didn't come out and say it, but she was there helping gather a lot of this data.
Excellent. All right, we got Shlomaya's in with us with the Indigenous Landscape Initiative in New Hampshire. Thank you. Very much of a regular on these student webinar series. We appreciate your support. Dan Ross is here from Somerset County Park Commission, New Jersey. Sharon as well from the U.S. Forest Service in Maryland. We've got Scott from Suffolk County DHS on Long Island. Great. Well, thank you everybody for joining us today. And so why don't we just go ahead and get started with Trevor. So Trevor, before you begin, please share a little information about your background and what you're working on and maybe anything that's coming up in the future for you.
Sure. So my name's Trevor, and you guys know that already. Right now, I'm an undergraduate at Columbia University. I am set to graduate in 2 weeks, and I'm very much looking forward to it. Prior to coming to Columbia, I was in the United States Marine Corps, where I mostly did administration and logistics. So transferring into environmental science and ecology was quite a jump for me, but I'm happy to be here. I'm very interested in parasites, parasite ecology, and vector-borne diseases. And I'm hoping to take that interest with me as I enter medical school this summer. So that's a bit about me. When I'm not doing research and school things, I'm mostly just relaxing with my dogs at the park and drinking too much coffee. So I guess if there's no questions about any of that, we can move on. So this is my project. As you know, it's about the impact of forest thinning or controlled fire on tick populations through the lens of how those disturbances impact host species like deer. My mentor for this project was Dr. Gallagher from Salis Experimental Forest down in the Pine Barrens. I don't know if any of you know him, but he's a very nice person to work with. And if you have the opportunity, I highly recommend connecting with him. So I want to discuss a bit of the motivations for this project. So vector-borne diseases have really skyrocketed in recent years, as well as zoonosis from vector-borne diseases. They've more than doubled from 2004 to 2016 for probably a multitude of reasons that really aren't well understood, and the CDC hadn't published at the time of my searching. Uh, there's a lot of tick-borne diseases of various kinds that evolve throughout the US in different places. But you can probably see from this map that here in the Northeast, we have the greatest risk of tick-borne disease in the country. So, this kind of combination of an increasing risk of vector-borne disease and zoonosis and our regional danger for these things were kind of a big motivator for me when I decided to pursue this project. On top of the health burden, there is a significant economic burden. Almost 500,000 Americans every year are diagnosed with Lyme disease. And there's an economic burden of this that falls between 345 and $968 million. This cost doubles for people with late Lyme disease, their cost of treatments. And none of these estimates acquire for other tick-borne diseases that are not Lyme disease or our recent zoonosis. So the need is pretty large. I want to talk a little bit about zoonotic emergence as well before we get talking about the ticks and the forests. So about 2/3 of human infections originate from pathogens that we share with animals. We focus a lot on managing infections that come from these spillovers once they have already spilled over into human populations. But what we've learned from recent events is that this can be very challenging to do, and it can come at a very large cost. So what I seek to do in my research more broadly is to try to identify a way to prevent these spillovers further upstream before they get into human populations to, maintain overall health and manage the health and well-being of people, the environment, and wildlife from a One Health perspective. So I want to talk a little bit about ticks. For those that aren't familiar, I don't know how many tick people are in here. There might be a few. I'm imagining you're at least somewhat interested if you are here. But ticks start their life cycle as these larvae. They're just little bitty baby ticks, and they generally have a lower risk of giving you any kind of infection until they feed on some kind of host, right? So the larval ticks need to acquire a host and take a blood meal, and then they'll go into the leaf litter and they'll molt over the winter and become nymphal ticks. And these teenage ticks have a higher risk of transmitting an infection to you because they've had the opportunity to have a blood meal. They will seek out a host and take another blood meal and molt to an adult stage, after which they will take a third final blood meal and reproduce. Somewhere along this way, they can bite people, they can bite people's dogs, they can cause infections in human populations. We're really not a good host for them because we can pick them off. So they tend to prefer animals like deer that have a large body size. They can get a good blood meal on them, and the ticks have a advantage of not being removed by the deer. So what the ticks feed on matters for the persistence of the pathogen in the environment. There are what they call reservoir hosts in tick disease ecology and amplifying hosts. Reservoir hosts are hosts such as mice or other small mammals that when they're fed upon by an infected tick, they more easily acquire an infection, but they also maintain the pathogen in their body at high enough levels where they can easily reinfect a tick that hadn't been infected yet. And in this way, the pathogen persists in the environment. Deer, on the other hand, as you can see from this diagram, are not to be considered competent hosts for most tick-borne diseases. However, they are critical for the maintenance of tick populations. So you kind of need to have both in order to have any kind of important number of questing infected ticks in the environment. There's a lot of work that shows that the number of infected ticks in the environment is associated with the degree of forestation, which can mean the degree of canopy cover or the basal area of a stand. And this is a very traditional way of viewing it. I think for the purposes of this project, it's more than sufficient, but I do want to touch on the fact that it does get a bit more complex, and there are a few other hypotheses that are interacting with these ideas. One of the big ones in disease ecology right now is this idea called the dilution effect. And the dilution effect is essentially a hypothesis that says that increasing biodiversity in an ecosystem may decrease the infectious, increasing the biodiversity of an ecosystem might decrease the propensity of a pathogen to spill over into novel hosts. Another idea with specific attention to ticks is that an increasing degree of non-competent hosts might contribute to a reduction in infectious vectors. That is, if you have more deer, you might get more ticks, but the amount of pathogen in the environment might be diluted by just the sheer abundance of non-competent hosts. I do not test this in my project. I just wanted to discuss it because it might be interesting for future research applications. All right, so on to the forests. Some of you might be familiar with this idea of massification. Essentially, it's this idea that without disturbance, a lot of forests in the Northeast, they tend to accumulate these shade-tolerant trees, such as maples, and in the sake of the pine barrens, this can really mean more oaks. And when these trees begin to dominate the ecosystem, the understory becomes cool and moist. These cool and moist conditions create an environment that is very conducive to happy and hungry ticks that are excited to go out and find someone to get a blood meal from. So what can be done about this process of massification? So there's some interest in exploring fire and thinning to reverse the process of massification in fire-adapted ecosystems. One of the advantages of this is also that it reduces the risk of catastrophic fire by reducing fuel loading. But this process might also create microenvironmental conditions that are less hospitable for ticks by creating warmer and drier microclimates. I wanted to see if these forms of disturbance would also be significant in influencing the land use behavior of deer because of their role in maintaining tick populations. And for this study, I chose the New Jersey Pine Barrens, which I imagine many people here are familiar with. Are there a lot of people from New Jersey here in the room today?
There are a few, Trevor.
Oh, so you guys know what the New Jersey Devil is, don't you? All right, well, you guys don't have to answer.
I got one thumbs up. Yep, there's a fire emoji. So
all right, well, I hope Dan Ross at least appreciates this little bit of humor, the masked New Jersey Devil. So the Pine Barrens are pine-dominated forests in southern New Jersey. There's a natural succession there from pine to oak, but that successional trend is maintained by a frequency of fire, which is significant and maintains pine dominance in the forest. It's also characterized by acidic and sandy soils that are extremely well draining, and these factors combine to make relatively arid microclimates that would usually be not extremely hospitable for ticks. Yet there are quite a lot of ticks there. And so that's part of why I wanted to explore this ecosystem. So here's a map orienting those who are not aware with the location of the Pine Barrens. Part of the forest is this preservation area where there really isn't much development. The rest is a protected area, but there is increasing human development there, and people are building new homes. People go there to go hiking and camping. So there is a risk of people interacting with ticks and acquiring a pathogen here as well. Um, so what's the difference between burning and thinning? So I conducted a literature review when I built this study, like everyone does for all good studies. And I kind of put together a Venn diagram here that shows some of these, what I would expect to be some of the similarities and differences in the outcomes of thinning and burning that I wanted to explore. Mainly the big differences based on the literature seem to be that thinning would contribute to an increased understory density, whereas burning would do the opposite, and they would have opposite impacts on small mammal populations. Now, again, I didn't have the opportunity to test anything related to small mammals, such as mice, in this study. Um, but I also hypothesized that they would both similarly have contributions to warmer, drier microclimates, reduce questing tick abundance, and they would potentially increase deer land use shortly after disturbance because of the increased browse. To conduct this study, I had a bunch of data on forests that the Forest Service very generously shared with me. Historical data from the Pine Barrens and the areas surrounding Silas experimental forests. So the stands were classified into groups based on the type of disturbance and the recency since the disturbance. So I wanted to have more thin stands. I was only able to get one thin stand. I wasn't able to get access to other thin forests. The burn forests were classified by early, middle, and late forest, which describes the time since they were modified, as you see on the map, 2, 4, and 9 years since the fire. And the purpose of this is to account for the average tick life cycle. Ticks usually mature over the course of 5 to 7 years, if I remember correctly. So the different time intervals allow to kind of create a snapshot of different stages of population recovery. In each of these different groups of forest, I established 3 10-meter diameter plots, and I gathered my data through the following methods. So at each plot, a monthly tick survey was done by dragging a 1 meter by 1 meter cloth flag on a 40-meter transect across the site. So the transect rotated at every sampling. So 1 month it might have been north and south. The next month it would have been northwest and southeast, and then west and east, etc. Deer visitation was monitored with game cameras on the edge of each plot that were fixed at around breast height. And a kestrel environmental data logger was hung 10 centimeters above the leaf litter at the center of each plot. This logged the humidity and temperature every 5 minutes. And then I had some historical forest disturbance data from the U.S. Forest Service, which includes things like the frequency of disturbance in the stands, the time since the last disturbance, what kind of disturbance being burning or thinning, and the basal area, the dominant species, all your normal forestry data. So when I did the analysis, I had some gaps in my environmental data because of some equipment failure. I ended up interpolating these because they weren't usually any greater than more than 2 weeks. A lot of the data from the tick surveys as well as the deer cameras was zero inflated, which is not incredibly unusual for tick data. So I assessed the use of zero inflated Poisson models or negative binomial models for each tick life stage. I did an AIC comparison, and it showed the zero inflated Poisson model was the most superior fit. And then I used that model to analyze the impacts of various environmental factors on the tick and deer populations. And we got some cool results, which is really the fun part to discuss here. So this is a box plot that shows how humidity has varied according to the disturbance groups that we discussed. Um, so essentially what this is showing is that forests that have gone longer since their last disturbance have higher average humidity than recently disturbed stands, which is consistent with the idea of massification over time, where as these forests go longer since disturbance, they become damper and more cool. The average humidity in the late and control groups was similar. So I think there's a point where it kind of becomes consistent. It was really interesting to me to find that the lowest average humidity amongst all the groups was observed in the thin stands, despite having had 5 years since disturbance, as opposed to the early stands. I didn't explore this in great detail, but I would say, based anecdotally on just having gone to visit these stands, it's associated with the degree of canopy cover. The thin stand had much more canopy reduction than the stands that were burned, just because of the severity of the burn. So that might be interesting for future research implications. So here are 3 plots that show the influence of humidity and temperature on the date of sampling for each of the samplings. So it's the influence of humidity and temperature on the number of ticks collected. So each point represents an observed count of ticks, and it corresponds to a specific humidity and temperature in the sampling day. The trend line is it's showing the predicted number of tick counts across adult nymphs and larval stages, according to the output of the zero inflated model. So there's this kind of positive correlation for adult and nymphal ticks that exists, especially after you get above like 95-degree humidity. I don't know. So for adult ticks, it seems to me that they're more influenced by humidity than temperature. It seems like this is kind of consistent with the knowledge out there about ticks. As they reach their mature stages, they kind of become more hardy. So the humidity might just influence their questing behavior more. The the kind of the noisiness of the line in the nymphal ticks indicates a bit more of a sensitivity to temperature and humidity, which is where like some of these cold spots or hot spots you might see a rise despite the increasing humidity. The larval ticks, the data was kind of inconsistent and noisy, and I think part of that is because of the really excessive number of zeros in the data, but also because when you sample larval ticks, you either get nothing or you get, 600 of them. So it really makes it difficult to do this analysis. But we do see this peak between like 80 and 90% humidity and between 50 and 60 degrees. That may indicate that there's just a sweet spot there for them. But I think the trend is much more convincing here for the nymphal and adult ticks. So I wanted to discuss also the presence of deer across the different disturbance groups throughout the course of the study. The highest deer counts were observed in the early and late stands. The early stands had been burned 2 years in the past. The late stands had been burned 9 years in the past. No deer were observed in the control stands, but this may have been because of the incredibly dense understory that really prevented meaningful imaging. But that density could also have restricted deer movement in the stands to begin with. Yeah. So this is my last plot that I wanted to discuss, and in my opinion, the most meaningful finding of this work. So on the x-axis here is the disturbance frequency, which just shows how many years had passed by on average for each plot since the last disturbance. Some were subject to fire thinning every 2 years, some every 5 years, etc. And on the y-axis for each graph, you see the adult, nymph, larval ticks, and the counts of deer. And there's an interesting trend here. This trend line is showing the output of the predictions from the zero inflated model. And the trend shows that in plots that have a disturbance frequency that exceeds 2 years, deer populations begin to surge, as well as tick populations. So this finding is kind of consistent with what you would expect based on just knowledge about the tick life cycle and the ecology of ticks as they relate to deer. Um, it also might have implications for the management of forests. So perhaps every 2 years, burning or thinning is the most effective way to control ticks if that is your goal. So some of the conclusions that I would like to discuss from this data. I thought I would be able to find that thinning and burning were different. I wish I had more thinning plots to analyze, but based on the data I have, I'm inclined to believe that thinning and burning have comparable impacts on microclimate and deer habitat use. Um, Deer habitat use is likely to overlap with changes in tick populations, which is what was expected. But the most significant response to this is from disturbance frequency, which is not what I had expected. I thought recency would have been more important. Adult ticks tend to be more sensitive to fluctuations in humidity, where nymphal and larval ticks are more sensitive to both changes in humidity and temperature. And the frequency of disturbance is more important for managing tick populations than the disturbance type. Some of the limitations of my work, battery failure and equipment malfunction did contribute to some data gaps, and interpolation is not a perfect process. Sampling errors while conducting tick sweeps may have contributed to the loss of some specimens. I gave this talk to some tick researchers and learned that a 40-meter transect was probably too long and may have resulted in some of the zero inflation in my data. If I had done it again, they advised stopping every 10 meters to check my cloth flag for tick specimens. The limited data on the adult ticks may have exaggerated the trend in the relationship with humidity. And the control plots may have had deer presence, but the density of the understory made it difficult to capture that presence on camera. If I could have done it different, I would have maybe attempted to do deer fecal pellet surveys as well to supplement the cameras. And that is about all I have to present on. I think I made pretty good time. I hope I didn't move too fast for everybody here.
No, that's very good, Trevor. Thank you so much. Before we get to some of the other questions, I have just a couple questions from myself. The when you did the tick surveys, the methodology of the sample area, and again, because I'm not familiar with this, like where you've got the camera, the Kestrel, and all that, is that when it comes to doing surveys, is that kind of like the standard operating procedure, standard plan to do tick surveys, or are there other methods?
To be clear, you're referring to let me go back to my figure. So
Like,
this idea of doing like dragging a flag along a transect.
yeah, is that like the standard methodology for doing tick surveys?
Yeah. Based on the majority of the literature out there, most researchers are using a tick flag and dragging it along a transect. Some people are just doing a very long transect, say if they are interested in the difference in tick populations across tree lines or trails. I'm really interested in what the population was like in these forest plots. But dragging along a transect is a standard. Some people do also use traps, which are interesting. And it depends on the species of tick you're trying to catch. For instance, you can build a carbon dioxide trap, which is essentially dry ice in like a modified 2-liter bottle. Um, but that only really works for ambyloma, the Lone Star ticks, because they're attracted to carbon dioxide. Um, you won't really catch deer ticks that way. So if you want to sample the environment, a transect is the gold standard.
Gotcha. Okay. And then the other, just a comment on, I agree with you about the thin stands and the lower humidity. I'm just thinking from a meteorological perspective. You talked about, less canopy, so that would allow more sunlight and help to, warm things up and lower the humidity. So meteorologically, that definitely makes sense. The way you showed the thinned areas have the lowest humidities out of all of those different areas. Yeah.
Yeah, I was interested to find that because I kind of thought that the presence of fire would contribute to a more arid environment. Um, and that was certainly true in one of my stands. But that seemed to me to have more to do with the intensity of the burn. So one of my stands had a stand clearing fire, a very severe one. But some of them were controlled burn, which is generally lower intensity. Um, if I could do this project or pursue it more in the future, I would love to find a way to um, do an analysis that also leverages the intensity of disturbance. Um, but I'm not sure if that historical data is available at present.
Okay, thank you. We've got a couple of questions here in the chat, and feel free if anyone else has any other questions to pop those in the chat. So Scott Campbell asked, did you see any deer sign in the control plot like prince or scat?
So hold on. Yeah, so prints are scat. Prints are kind of hard to see in the pines, often because of the very, very sandy soil. Um, I didn't see any prints personally. Now scat does stay for a while because of how arid it can be there. Um, but this understory is very dense. And I mean, it's difficult to get through unless you're exactly on the trail. I didn't see any personally along the trail. Um, and some of the brush in the understory is this very woody, dense, ericaceous, like shrub stuff, like huckleberry and blueberry. Um, I would see I couldn't see how the deer would have a very easy time getting through it to defecate. Maybe other parts of the plot, but I didn't get the chance to get over there and see it, to be honest with you.
Yeah. Hope that answers your question, Scott. We've got another one here from Shlomaya. I've been taught that ticks exist more in open grassy fields, particularly tall grass. Is that incorrect? Or how does it relate to ticks liking the cool, moist understories of mesified forests?
Oh, it's definitely true that ticks like the tall grass. Um, and they have similar uh, ecological interactions with these deer and mice that also hide in tall grass areas. They have a lot of these problems in prairies. Um, so the understory of these tall grass prairies, though, is still relatively moist and damp, just because, I mean, I am not super well educated on prairie ecology or anything like that. But I would expect that just with the density that grass grows and how tall it can be, which is certainly tall enough for ticks to hide in the understory of a tall grass prairie, um, that it would still be cool enough and moist enough for them just because of the density of growth. Uh, Does that answer your question? I don't really know as much about that ecosystem, but I do know that ticks do certainly thrive there as well.
All right, here's another question from Amanda. Thinking about humidity and microclimate, during your field season, was humidity lower or higher than normal? Or does that matter to ticks at the microclimate scale?
Oh, that's a good question. Oh, you're welcome. So I don't know if I would say it was higher or lower than normal, um, because I didn't consider that benchmark, to be honest with you. But it didn't seem notable to me. I mean, we can see that humidity kind of remained on average between 80 and 90 based on this plot that I have here, the box plot, with some exceptions that went much higher. Um, if somebody knows if that's the normal range for the New Jersey pine barrens in the summer, um, I'd be interested to have you chime in. Um, I think at the microclimate scale is the most important thing for the ticks. Um, so there is meteorological data that would show the humidity above the forest, and maybe I'll do that comparison now that you suggest it. But what matters to ticks most is the humidity at about the height of the leaf litter or shortly above it. So maybe the reason I hung the kestrel loggers at 10 centimeters above the leaf litter is because it's the humidity at that level that's going to determine most their tendency to go quest for a host.
I know, just adding to the humidity before Amanda's follow-up comment, like with the National Weather Service, when they have their observing stations, it's usually their sensors are anywhere up to, I think, 33 feet above ground. So they would definitely, whatever long-term historical meteorological data you would get would definitely not be the area that you're trying to sample. It would still give you a general idea, but it did definitely nothing that low to the ground.
Yeah, I that was really the advantage of using the data logger. I can show pictures of these plots. I feel like uploading them all to this might take some time away from answering other people's questions. If you would prefer, I'm happy to leave my email in the chat and I can.
Or maybe if you just had like one photo, we still have a little bit of time left.
Yeah. So are you guys more interested in seeing like the control plots? Um, okay, sure. Uh, Let me plug in the hard drive.
And so while Trevor's doing that, I can just kind of mention that, as I said earlier, this is the final student webinar series presentation of our spring session, but we will be doing this again coming up in the fall of 2024 and also in the spring of 2025. So if you or somebody else you know would be interested in sharing your work, please reach out to me, and I'd love to hear from you. And we can go ahead and schedule something. I'm going to drop into the chat right now just our link to our student webinar series page. And these, most of them are recorded. So if you wanted to go back and see what we've done in the past, you can view those. And but again, there's my email if you wanted to reach out, and we can chat more about that.
Yeah, sorry about that, everybody. My computer bugged out. Um, but I was able to pull up a photo archive. So if people are still interested in seeing these plots, I can share a bit.
Yep, feel free to go ahead and do that.
Okay. So
Trevor, I put a comment in the chat while you were off that I asked about seeing the plot photos because it can help us to visualize the conditions that you surveyed the ticks in the years post burn and in the thin stands. The graphs were great, but sometimes a picture can be worth 1,000 words, and it's easier to see. Oh, I could see why there's more air movement in the thin stand, or I see what you mean about the understory vegetation and how that looks like grasslands. To Shlemaya's comment. So thanks for sharing the photos. Sorry for the
yeah,
extra request there.
no, not a problem at all. And I was trying to find a way to shoehorn them into some photos into the study without bogging down the PowerPoint, but I'm happy to share it. So I used this proprietary online software called Deer Lab that's targeted towards hunters for game camera analysis, just to sort through. As you can see, I had quite a lot of game camera photos. Um, So I'll show you guys. This is one of the control plots, the reference forests that weren't managed for over, they haven't been, this one hadn't in particular hasn't been burned for over 20 years. So these tags are a lie. This thing is kind of an imperfect product, but it did whittle things down for me a bit. But you can see, say if I put it on deer, this is one of the control plots, and it seems to think this pole in the middle of the plot is a deer, so it takes a bunch of pictures of it. In fact, there are no deer in this plot that ever showed up on camera anyway. But you can see how it has this really like woody, dense understory growth. A lot of this is like huckleberry, blueberry. Um, you get some laurel, some mountain laurel. So it really makes movement quite challenging. Um, and when I tick drag this plot, dragging over the top of these brushes also isn't a great way to get ticks because some of these are way too high for them. I ended up brushing the understory in all the plots too with the flag, just to see if I could get any samples from down underneath the shrubs. But yeah, so this is an example of one of the control plots. And then,
Oh, so just to comment a little on the structure, then this is really helpful to see. So there's not a lot of daylight getting in there, which makes me think it's a fairly dense stand and also more canopy cover. So thinking about how that affects the ticks and how that retains the humidity. So it looks like that would be a stand that holds some moisture in it.
oh, certainly. Yeah, this was perhaps my least favorite one to go into. Because I mean, you just get chased out by Lone Star ticks. They're throwing you out the door. Um, or rather not letting you leave. Um, but yeah, that is the exceptionally undisturbed one. That one had gone for over 90 years without fire or thinning, as I understand it. Um, but if I show you perhaps like one of the thinned plots, here we go. So you can see how there's quite a big difference in the amount of canopy cover and sunlight coming through in the thinned plots.
Yeah, that would be a huge difference in microclimate.
Oh yeah, and it definitely was. Um, and then give you an idea. So this is one of the early burn plots, which is the ones that were burned maybe 2 or 3 years ago. Um, but it's low severity, just understory burn, to clear it. You can see how there's some of these burn scars on the bottom of the trees. But it didn't really modify the canopy structure that much. So it still stays pretty cool in there. But there's much less shrubby understory for anything to hide in. The deer love this plot, by the way. So the deer were here a lot. I think I have some good deer photos from this one.
Can you remind me the height of the kestrel again?
It's about 10 centimeters.
Ah, okay, so that's super close to the ground then.
Yeah. And then for an example of, say, the middle range plots. Sorry, this takes a second to load. So I think Red Oak was one of my late ones, if I remember correctly. Chatsworth. Yeah, this is a middle range plot. It was burned maybe 4 years in the past, if I recall correctly. So you kind of, let me verify that this is in the middle range. I have a, why is my computer so laggy?
So this definitely looks more palatable than the control plot, but still, I'd want to be wearing a lot of permethrin going around that stand. That's still.
Oh yeah. Yeah, we were. Yeah, I mean, there were ticks for sure. Yeah, so this is Chatsworth. This is a medium classified plot, which means it's been about 4 years since this one burned. And to give you an idea of a late plot, which is about 9 years since the last burn, I'll show you red oak. Yeah, so this one actually had a lot of activity. It looks a little bit less dense, but the canopy was much there was more canopy cover here. So I really got beat up at this plot, and I think another one would be, I suppose, Lacey and Webb's Mill.
So Trevor, I know you said you had a little time crunch, so we're right up to that time when you kind of needed to
Oh, sure. Yeah.
close this up. So anyways, great call, Amanda, on asking Trevor to show these. And Trevor, I'm glad you pulled these in there because yeah, that was a great addition to the presentation. So thank you so much for adding that in there. And so again, thank you, Trevor, and everyone to attend your talk today. It was very informative, and I know everybody appreciated it. And so again, thank you for participating today, and thank you all who were on, and look for us in the fall of 2024 for another student webinar series. So thank you again, Trevor.